Hi everyone, welcome back to Math 261. This is Scott. Let's get started. What we are going to be doing now in section 5.4 is looking at the relationship between eigenvectors and linear transformations. Alright, well first what we're going to be doing is just looking at linear transformations on their own, and then we'll bring eigenvectors into the mix. So here's the setup. What we're going to have is T is going to be a linear transformation. From vector space V to vector space W. Now if B is a basis for V, and C is a basis for W, then we can determine the effect of T based on what it does to the elements of B. Alright, and this is a general fact actually about all linear transformations. If in the domain of the linear transformation we have a certain basis that we're using, then what we can do is we can always figure out how the transformation is going to behave based on what it does to the elements of the basis. So in particular, we can make a matrix out of the linear transformation. We can make a matrix for the transformation. Relative to B and C as follows. So this is called the matrix for T relative to B and C, and we'll use M for matrix. So M is equal to T of B1, and it's going to be the representation of that relative to C. Then we're going to have T of B2, representation of that relative to C. Dot 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 until we get to the last one. Let's say N. And we get that relative to C. All right, let's see what this would actually look like. This looks very hard to get a handle on. Is this actually difficult or is it easy? So in this class, usually the harder something is to understand from the notation, the easier it actually is to do mathematically. So let's see what this actually would look like in practice. So as an example, so the first type of example that we'll have here is we will be given two bases and we'll be just told directly what the image of each basis element from B is based on C. So if basis B, let's say, has three elements, B1, B2, B3, and let's say basis C has two elements, C1, C2, then let's say that T is defined by T of B1 is equal to, we could say something like C1 minus C2. And let's say T of B2 is defined to equal something like, let's say, 3 times C1 minus C2. And then let's say that T of B3 is just equal to 2C2. So no influence of C1 there. Well then, looking at this matrix here, we are supposed to be finding the representations of each of these elements relative to C. Well, what does a representation relative to C mean? That just means that you take this expression here and you express the weights of each of the basis elements as coordinates. So C1 has a weight of 1, a coefficient of 1. C2 has a coefficient of -1. Similarly here, if I want to take T of B2 relative to C, it's going to equal 3 as the weight on the first, -1 as the weight on the second. And then lastly, T B3 expressed relative to C just separate these out a little bit, is going to equal 0 on the C1 and 2 on the C2. So what we've made here are the three coordinate vectors for the images of the elements of B, each relative to C, and now each of those is going to be the column, corresponding column of M. So it's going to be 1, -1, 3, -1, and 0, 2. So this actually, although the language of it is very ornate and difficult to get your head around, perhaps the actual operation here is very easy. You would just express each of these as coordinate vectors, and those coordinate vectors in turn would go into making the columns of M. Now this is sort of the most abstract or general formulation of this, but what's going to happen more frequently in practice is that we'll be talking about a transformation not from one vector space to some different vector space, but more frequently just from one vector space to itself. So, note. we will frequently look at linear transformations from a vector space to itself. So in other words, T from V just into V. When we use the same basis for V, both before and after the transformation, then we will refer to the matrix. So then, if we use the same matrix, or sorry, same basis, before and after, transformation. So in particular, the matrix in question would be M, which equals T B1, and now would be represented relative to B. To TBN, still relative to B. So if we use the same basis before and after the transformation, M, which equals this, is called the B matrix for T, or the matrix for T relative to B. Alright, now let's see an example of how this can look. So then, if we have a transformation from R2 to R2, and it's given by the matrix Tx, which is equal to -1, 4, -2, I'll say this matrix, -1, 4, -2, 3 is equal to matrix A, and T of x, by definition, is going to be multiplication by A. So this represents the matrix for the transformation in the standard basis. But if I choose some other basis, so let's say that B1 is equal to 3, 2, and B2 is equal to -1, 1, and B is equal to those two vectors, 3, 2, -1, 1, then the task would be find the B matrix for T. Alright, well now let's think about what this actually would mean. This would mean we would have to find the representation of B1, sorry, the image of B1 under T. So let's first figure out what the image of B1 is going to be. So B1 is going to be A, so T of B1 is going to be equal to A times B1, which is going to equal -1, -2, 4, 3 times B1 times 3, 2. Which is going to give us -3 plus 6 is going to equal 3. We have -6 plus 3. Sorry, -6 plus 6 is going to equal 0. And now what we need to do is figure out the representation of this relative to the b's. Now before we do that, while we're at it, we might as well also find the image of B2. So it's going to be A times B2. And what we're going to have here is going to be 1 plus 4. So that's going to equal 5. And here we're going to have 2 plus 3, and that's going to equal 5 as well. Oops, correction here. So this is going to be -3 plus 8 is going to be 5. 5, 0. Okay, so those are the two images of the elements B1 and B2. And so now let's think about what we're supposed to be getting. We're supposed to be getting the representations of those. And if you think about that, that means that we are find T B1 relative to B and T B2 relative to B. But what each of these means is that we have to set up, in this case, an equation. That's 5, 0 is equal to PB times the mystery TB1 with respect to B. And 5, 5 is equal to PB T of B1, sorry, T of B2 relative to B. But both of these are then going to be where P of B is the same matrix in both. Both of them are going to be the B matrix, so 2, 3, 2, -1, 1. And we can solve both of these. These are both systems of equations that we can solve simultaneously. Solve both together. So we'll have 3, 2, -1, 1. And we're we're going to augment it with 5, 0. So just solving this will tell me the representation of t of b1. And then I'll augment my augmentation with a little more, the 5, 5. And I'll row reduce this, and what I will get, now I can appeal to technology to come to my aid. And what I get when I set up and row reduce that matrix is the following. So I get 1, 0, 0, 1. So in other words, just the identity on the left. 1, negative 2, 2, 1. Which means then that our M is going to be, well, the first column is going to be the representation with respect to B of t of B1, which is going to be the 1, negative 2. And then the second column is going to be the 2, 1. Now notice something, the procedure that we used right there was in fact the exact same procedure as what we have done once before, and that was for finding a change of basis matrix. So note, this process is the same as finding P, and let's see, so this one would be with B on the left and C on the right, where the C here would be very specifically that A times B1 up to A Bn. So you apply A to the basis B, and that produces a new basis. And then the change of basis, that is the change of basis matrix that we would be producing in doing that, will actually be the same as what we get here for the B matrix for the transformation T, or for the matrix A. Now, one more note, so eigenvalues and eigenvectors, or in particular, let's say eigenvectors. So if let's say bi, so just a random element, happens to be an eigenvector of A, with eigenvalue lambda, then A bi by definition is lambda bi. But what that then means is that the representation of ABI is actually going to be zeros everywhere except for entry I, where it will be lambda, then it'll be zeros everywhere else, where this is entry I. Now, what is that going to mean? That means that in that particular column anyway, the only entry that's not guaranteed to be 0 is the entry that's along the main diagonal. So this means, thus, in that column, of the B matrix of A, there are zeros except along the main diagonal. Now let's think about what that then means. Well then, let's suppose we had a basis that was all eigenvectors. So if we have an eigenvector basis for Rn, then the B matrix for A will be diagonal. So if every element in the basis is an eigenvector, then the whole matrix will in fact be diagonal. All of the entries will be 0 except possibly along the main diagonal. So what that means is then if A is diagonalizable, then by definition that means A equals P d P inverse, where, as we saw last section, P is the matrix whose columns are the eigenvectors of A, and where D, which is diagonal, happens to also be the B matrix of A relative to that eigenvector basis. Sorry about that, I had to reshoot part of this due to a technical malfunction, and so I wasn't able to keep the part of me writing along here, but I'll give you a chance here to catch up. So then, if we have an eigenvector basis for Rn, then the B matrix for A will be the diagonal matrix that we used to call D. And if A is diagonalizable, then that means that what we have here is a recipe where P is the standard B matrix for this basis that you get by making the columns out of the elements of the basis. Out of the eigenvectors of the basis, and then D is the diagonal matrix that in this case also turns out to be the B matrix of matrix A. So as an example of how this could end up looking in your life, what you might get is a matrix, and then you would try to find a basis relative to which this matrix is diagonal. So as an example, let's take a matrix A is equal to -4, 7, 1, and 2. And then the task would be find a basis if possible relative to which A is diagonal. Or I should say, actually, A is that T of X is equal to AX, and I'll say relative to which T is diagonal. Okay, well, what it all amounts to is determining whether A is diagonalizable or not. So, to determine that, what we need is to look at the eigen situation. So we'll look at A minus lambda I, which is the standard setup when considering all things eigen. So that's going to be subtracting lambdas from along the main diagonal. Alright, now the characteristic polynomial It's going to be what we get by taking the determinant of that, which you can write det, or you can just write it with the absolute value bar. I guess I'll write det. And we'll set that equal to 0. That makes it the characteristic equation. And now we actually will multiply this all out. So we're going to have a lambda squared. We are going to have, so we're going to have positive 4 lambda minus 2 lambda. So it's going to be a total of plus 2 lambda. And then we're going to have over here minus 8 subtract 7 equals 0. Now it's going to be lambda squared plus 2 lambda minus 15 equals 0. And remember, by the way, one of the shortcuts we could have used for this 2 by 2 case would have been the determinant of the matrix here and the trace of the matrix, the negative trace of the matrix right there. But it's not necessary to do that in the case of a 2 by 2 because it's so relatively simple anyway. But anyway, so now we would factor this if we can. If we can't, we'd use the quadratic formula. But we can, so it's going to be lambda plus 5 times lambda minus 3 equals 0, which gives us lambda equals negative 5 or positive 3. Okay, well, the fact that this has two distinct eigenvalues means that we don't have any repeated eigenvalues, so we don't have any chance for any of them to be defective, which in turn means that there is no chance that we are lacking any amount of the eigenvectors that we need. Each of these is entitled to at least one eigenvector, and so what that means is we are guaranteed to be able to diagonalize this matrix. But let's find the eigenvector basis that would make this happen. So for lambda equals negative 5, that means a minus lambda I would equal, so it's going to be negative 4 plus 5. It's going to be 1, 1, 7, and 7. And looking at this, we are going to have a very easy time row reducing this one. So augment the zeros, row reduce, 1, 1, 0, and I can already tell it's going to be 0, 0, 0. So what this means is x1 plus x2 equals 0, which means x1 equals negative x2. x2 is free, so it equals itself. And then that means that we're going to have a v of negative 1, 1. So there's no reason for me to go around picking anything too creative for x2 here. Just the value of 1 will be good enough, and that gives us an eigenvector of negative 1, 1. And then if we repeat, but for lambda equals 3, then a minus lambda I is going to equal, so we again just look at this and put in a 3, so it's going to be negative 7, 1, 7, and then down here we're going to have negative 1. And we can see how that's going to go. So we can negative 7, 1, 7, negative 1, 0, 0. I don't need to RREF this, just getting it sufficiently good that we can actually read off what we need from it is fine by me. So here we can just clear out the top. I don't like that negative. Basically, you can think of it as scaling it by a -1 here. And now let's think about what this means. So this means 7x1 minus x2 equals 0, which means 7x1 equals x2. So a possible solution here could be x1 equals 1, x2 equals 7. That would work. And so then that means a v of 1, 7 would do the trick. And here, this is not by any means unique. We could just as easily have given it a different value. But now, since we have these two eigenvalues, eigenvectors, we can state the eigenvector basis. So the basis will be, it'll be our first one, which was, what was that? It was -1, 1, and 1, 7. And relative to this basis, we would have the B matrix, which is diagonal because these are eigenvectors, and in particular they would be -5, 0, 0, and then 3. Okay. So that is the relationship that diagonalization, and in particular eigenvector bases, has with linear transformations. In section 5.9, we'll see another and actually even more intriguing relationship that eigenvector bases can have for a specific linear transformation, in particular what will be called a transition matrix. But that'll be a lesson for another day. So for now, I'll see you in the next episode of Math 261. Till then, bye.